Okay, let's start the video now and study somehow, mathematically challenging topic in chapter 3. This is called the continuously varying payments streams. Uh, Obviously, you can think this as a very special annuity. What's different from what we studied is now you actually allow both the rate and force of interest to be continuously varying functions. So before we always assume this is constant, right? And the payment rate, we studied two cases. It is either a constant or a piecewise constant. What do I mean by piecewise constant? So let's say this is a rate. We use low to denote. In section 6, we studied, not section 6, section 5, we studied continuously payable varying annuities. One of the example we studied is continuously payable of $1 in year 1, okay? And then it goes to $2 in year 2. So this is 2, and then $3 in year 3. It is not a constant, obviously, and but we can call this type of function a piecewise constant function, right? For this particular piece, it is a constant. It's a constant at 1. And then for the next year is another constant. It's a constant at 2. For the third year, it is yet another constant, but now at 3. How about we consider something like this? Right? Or we increase like linearly. Right? There are many different possibilities. For those two blue lines, right, or blue curves, it's easy to see they are increasing, meaning as time evolves forward, the payment rate increases. So in those cases, we deal with continuously payable increasing annuities, except that now how the rate increases is captured by a function which we call low. Now low is a lot more complicated because it may not be piecewise constant, right? It can be something quite complex for you to model. And another thing is the force of interest is delta t is no longer a function. Is no longer a constant. Now it becomes a function of time t. So as time changes, the rate will change as well. When it comes to discounting. So in this section, we deal with quite general cases. We don't make a lot of assumptions on rho and the delta. So this is rho, RHO, rho. This is delta, DLTA, delta, like airline delta. So now let's take a look at the setup. So what we first need to study is the PV factor. Okay, this part we actually studied in chapter 1, right? When we study the time value, we studied simple interest, we studied compound interest, and the last one we studied is force of interest or continuous interest. In that case, we studied this general form. So this delta can be a non-constant, but of course, so this means this is not exactly equality, which means on the left-hand side you have a function. So on the right-hand side, there's 3 horizontal lines. That means for all t, this is delta, so it's a constant. So if the force of interest is a constant, what do we have? Then this is what we used to have, right? In particular, we often like to calculate the present value at time 0, right? So if you further set a to be 0, then this is the discount factor, which we are quite familiar of, right, at this moment. A is what we call the present time. In most examples, A would be 0. But here, A does not have to be 0, right? You can calculate the present value at a different time. Let's say you have some annuity, which is deferred by 2 years, right? So you start everything from here. And maybe you want to know the present value at 1 instead of at time 0, right? In such a scenario, A would be 1. So basically, you can think A as the present time. So this is the somehow a more general form of discounting or general form of PV factor. So here we can have a function for delta. I believe we did several examples in chapter 1. So if you forgot now, maybe now is a good time to go back to review this PVF. What's more different right now? It's we do have continuous payments, which somehow we already studied in a few cases. What's more difficult is it's not only the payments, they are continuously payable now, they are continuously varying. So the rate is changing. Like before, what you can think of is you set up a cruise control and let your car to drive itself at let's say 65 miles per hour. Right? It's the car drives at a constant speed, 65. Okay, but now you don't do that, right? You control everything. Sometimes you might be at 60 miles per hour. Sometimes you might be going a little faster, 70 miles per hour. Your speed right now is not flat. The easy case is you have a flat speed. Then if you know, let's say your speed is 65 miles per hour. If you travel 1 hour, of course, you know the distance you have traveled is 65 miles. Now your speed is like this. Okay, then calculating how far you have traveled is more challenging, right? Then what you need to do is to do an integral. Okay, now let's do a quick analysis on how this um, can affect the computation. Okay, so again, this is rate. For any rate to convert into amount, you need to have a time interval. So let's say it goes from t to t plus delta t. Delta t is a small amount of time. Let's say 1 minute, 2 minutes, etc. Right? So the speed or the rate times the time interval is approximately. You see the word I use here, approximately the speed or the rate times the interval. I use the word approximately. That is because even over this small interval, the rate is changing, right? At the starting point is low t, and then as time moves by, it becomes low s. At the end point, it becomes low t plus delta t. So even for this small time period, the payment rate is changing as well. But because this delta t is very small, using the starting rate is somehow quite accurate because the rate is small. And here we will apply a quite smooth function for low t. So what I mean is, so let's say this is the function of low, somehow increasing, okay? So let's draw a timeline here. So let's say here is t, here's t plus delta t. So technically what I'm looking for is this area. Okay, this is somehow irregular area, right? So I have 3 sides, which it's either vertical or horizontal, but this line is difficult to somehow measure, right? So that's why we can use the left end. Here is low t. Let me get a different color. So I use low t. So if I draw a parallel down here, so what I do is I use this rectangle to approximate this irregular area, right? Because the height is rho t, the width is delta t, right? Because it will be the right endpoint minus the left endpoint. The distance, the interval of time is delta t, right? So obviously, for this special rectangle, the area is rho t times delta t. And now it's time for you to imagine the process of making this delta t smaller and smaller. So by using a small and smaller, partition, I move the right-hand side vertical line towards my starting point. This is my starting point. Okay, so once those two vertical lines becomes closer and closer, this area becomes smaller. And you can see, right, although right now it's underestimation, but as delta t becomes smaller and smaller, gets eventually or converges eventually to zero, the approximation is actually excellent, right? So that's why, I use the left end, but, you can also apply the right end. You can also apply the right end point to approximate. In fact, you can apply anything in between to approximate. You will get the same result. That's Riemann calculus. So that's the idea, right? So the amount within this small period is rho t times delta t. This is the amount. Okay. For this payment amount, we want it to be converted at the starting time. In this case, the starting time is t. So I will need to apply this PVS factor to convert this amount from t to a. So again, I should mention that this amount is not exactly paid at time t because it's continuously payable, right? So this amount is paid between t and t plus delta t. But since delta t is very, very small, I can think this continuous payment as a single point, with this amount. And then I discount back to a. So this is the present value. So this is the PV for this tiny interval. Okay. Of course, that's not the end of it. This is only the analysis. Now I want to look at from A to B, which means I'm going to separate this into many small intervals, each with the same width, that is delta t. Here I separate the entire B to A into n equal sub-intervals. And for each sub-interval, I apply what I just did. I use rho times delta t and then times the appropriate discounting factor. So when the number of sub-intervals goes to infinity, that means delta t goes to 0, I will get this integral form. By the way, this is how you define calculus. So again, the concept might be a little challenging to understand because some of you may be taking calculus at the same time, or you have never actually learned the formal definition of integral. Then this kind of limit to take the first two partition and then to take the width of each partition to 0. The idea, can be somehow abstract for you to get any understanding. But anyway, what I can somehow summarize is rho t delta t. This is amount, right? The amount at time t. And in order to get this amount to time a, or the present time, you need to times by a discounting factor. This is the continuous discounting, okay? And this is only for a single, period. Now you have many periods like this. So you're supposed to do summation as what we did before, right? But we know the limit case of summation is integral. So this is somehow naive interpretation of these results. Now let's use a few examples to help us understand the meaning of this general result of present value. As mentioned, here it's rather a general case because both the payment rate rho t and the force of interest delta t can be functions. But we know a constant is a special function, right? So let's set this to be 1, delta to be 1 as well. Okay, not 1. 1 is too big. So let's put this to be a constant, delta t to be delta. So what do we have? Then this becomes negative delta. Let's assume A is 0, B is n. So assume A is 0, B is n. Right, and what do we know? Right, e to negative delta is exactly the 1-year discounting factor v. This is I need to put a bar. So this is A bar angle n. So that is the present value of a continuously payable annuity for n years. So as we can see from this special case, what we study in this particular section is a generalization of a standard continuous payable annuity, right? So here we make generalizations along 2 different directions. First, we allow force of interest to vary. Second, we allow the payment rate to be a function instead of a constant. So let's do some examples. 3.12, so that's page 81 if you have the textbook. Calculate the present value at time 0, so A is 0, of a continuously payment stream made at the constant rate of $25 per year from time 0 to time 10. And the force of interest, it is also a constant. By the way, this is the rather special case I just mentioned, but let's apply our result from the previous slide. So now I need to times by the corresponding discounting factor from 0 or from A to T, delta T, which is 0.04 ds. So put this into a different argument rather than T because we have actually 2 different integrals. This is the inside part. Put the inside part to be something with respect to a different argument. So here I use S, you can use something different. Right, and then we can easily get the result. So here's from 0 to 10. So what we have is 25 divided by 0.04. Then I have 1 minus e to negative 0.4 times 10. Right. So of course you can compute. By the way, from here, what we have is, so let's factor out this 24. We know e to negative 0.04 is 1 year discounting factor, and raised to the power of 10 divided by 0.04 is your delta. Okay, so what's this thing? Inside the bracket is exactly right. It's exactly the A angle 10, right? A bar angle 10. Okay, this is the present value of a continuously payable annuity with unit payment for 10 years. So that's why we just mentioned in this section, what we do is a generalization of a continuously payable annuity. 3.13 now is more complicated because the payment rate is 5t plus 1. So obviously it is increasing. Right? At time 0, the payment rate is $2 per year. But immediately, in the next second, let's say you assume t is 1. So in 1 year, the payment rate becomes $7 per year. In 2 years, the payment rate becomes $12 per year. So you can see it's increasing, and the force of interest is given by 0.1t plus 0.04. Okay, so this is also a non-constant, right? It's increasing as well, and time a is 0, b is 0.5. So we want to know the present value. So from A to B, rho t 5t plus 2 exponential of negative from 0 to t delta t. So put s for t and write as ds and finally dt. Okay, so obviously we're going to do the inside part. For this, the antiderivative will be 0.1 s squared divided by 2 minus, okay, I put the minus inside, or you can leave it outside. 0.04 s, so s goes from 0 to t. Okay, so that is the antiderivative of the inside integral. So now let's do the computation. It will be 0.05 t squared minus 0.04 t dt. This looks quite complicated, right? You have exponential, and the exponential of a power function. This power function is in order 2. The highest is 2, and the next one is 1. If you look at this part of the integrand, this is order 1 and then order 0. It's exactly 1 less than what you have in the exponential, right? So that motivates us to consider this, replace the complicated part. Okay, then we want to put everything into u. So first we need to know what is du. Du would be negative, we differentiate on the right hand side, 0.01 t minus 0.04 dt. Okay, well, if you are good at numbers, you can tell this and this, they only differ by a factor. So if I take out negative 50 or 1 over 50, the inside would be 5t plus 2 dt, right? So this part we have. So now with this in mind, we can go from, the textbook didn't change the integration endpoints. Usually I don't like that. So what I usually do is, remember this is the interval for t. Now we want everything to be expressed in u. So I will change this as well. So if I plug in 0 here, I get 0 for u. If I plug in 0.5, what I will be getting is 0.0325. Okay, now I have du, because du equals the whole thing, and negative 50, because we can write this 5t plus 2 dt equals negative 50 du, right? So I use negative 50 du to replace 5t plus 2 times dt, and the exponential is just the exponential u, right? So let's move this together. Okay, now, right, to do is it's very easy. It's negative. This number is negative 0.3.5. Then I get the result, right? It's 1.5989. Okay. What else? We do have one more, 3.14. 3.14 is actually a lot easier, because again, it's a constant for delta and rho, but now what's different is you start from 2 to 6, so the payments start from 2, and so I don't have too much space down here, so let's use additional page to analyze 3.14. The setup is actually easy because it's a constant $5 per year, and the delta t is also constant 0.03. But the question is, let's draw the timeline. We want the value to be evaluated at time 0, so we want to find the present value at time 0, but the payments is actually from 2 to 6. Okay, the continuous payments is from 2 to 6 per year. Okay, not from 0 to 2, not from 0 to 6, excuse me. So there is a little confusing part. There are a few things you can do. So first of all, you can first calculate the present value at time 2, and then you back everything to time 0. Right? So let's try that first. In that case, it is from 2 to 6, starting point to the end point. Rho is a constant, e to negative, the starting point is 2. Now I want t, delta ds, dt. By the way, what I'm calculating is the PV at 2. Okay, so that's why, when I do the discounting, the starting point is 2, not 0. Okay, so here's 265 e to negative 0.03 t minus 2 dt. Okay, if you want, you can do one more change of variable. So, okay, you can use something to replace t minus 2, then it's from 0 to 4, 5 e to negative 0.03 t dt. So it's 5 divided by 0.03 is 1 minus 0.03 times 4. Okay, this is only PV at 2. Now I want PV at 0. So this will be PV at 2 times by e to negative delta times 2 years. Right? So I first calculate the PV at time 2, and then I discount everything back to time 0. So this is one way to do it. There's a different method. We can directly calculate PV at time 0. Okay, so first of all, your outside integral is from 2 to 6 because this is the time when you are being paid continuously, and the rate is $5 per year. The different part is, so let me get blue color to highlight the difference. So now when you do the discounting, so it's somehow down here, right? So let's say t plus delta t, you have a payment which is 5 times delta t. For this, you need to discount all the way back to time 0, not to time 2, although you start receiving payments at time 2. But now we want the PV at time 0. So we are supposed to discount everything back to time 0. Okay, then you can see, it's the same thing, right? Because here it's for this is t dt. Right, so when you plug in everything, you can see. So you have additional discounting factor now. That's because when you divide by this, it will be e to negative 0.03 times 2 minus e to 0.03 times 6, right? So you can easily factor out the discounting factor for 2 years, and then what's inside will be 1 minus e to 0.03 times 4. So obviously, those two methods will give you the same result. That's probably we do have something for the present value. Okay, so for the accumulated value, excuse me. So basically, what you do is you still figure out the payment, which is low t dt. Okay, so when I draw the timeline, here is t, here is t plus. So this is very small, so I consider this as a point. Low t dt is the amount at this point. Now I want my value to be accumulated to the final point, which is b, right? So how do I get from this time t to time b? I will need to times by an accumulated value factor. Let's say from t to b, then it will be exponential from t to b delta s ds, right? So that's why you can see as inside part is the accumulated value factor when you have varying force of interest delta t, okay? And then of course outside is still the payment part from A to B. I do one question, okay, and then I leave another one to you to complete. Let me do the more complicated one, because this case, the accumulated value at time 8 years, so B is 8, of a continuously payment stream paid at the annual rate of 100 times e to negative 0.04 times t. Okay, so let me be careful. So I want my accumulated value at time 8, but this payment is only from 1 to 5. The force of interest is a constant. Okay, so now let's do the AV at 8. So similarly to what I just did, right? In this case, the payment is made between 1 and 5. So the integral is 1 from 5. The payment rate, so let me write dt. So I have just figured out the payment amount now. For this particular amount, I need to discount, or not discount, I need to accumulate to time 8. So here is t, right? I need to go from t to 8, delta s ds, right? So I move from time t to sometime in the future. So when I apply the exponential, it's going to be exponential of a positive rate, right? If I do discounting, it's negative. So that's something I want to mention here. You see here is exponential positive. In the previous one, it's exponential negative, right? So negative means discounting, positive means accumulating, okay? So then it's a calculus question, right? So you can factor out this, okay? And here you can write 0.028 minus t dt, and then well you can collect like terms to write it as 0.16 minus 0.060 dt. Okay, from here, well, obviously you can apply, let's say, well, you can first of all you can take out this constant part, and then it's an exponential function. So you easily know you just need to divide by whatever you have in the this part. Right, and then you will get the result. So please finish 3.15 as well. It's actually easier because both are constants, so it's an easy case. So let me stop here.